Hello everyone, in this video we are trying to make ourselves familiar with different algorithms presented in Earth Engine. Some things related to this content have already been uploaded in the previous videos. This video will be quick and very short guide to understand different algorithms present here. So the very first things to know is that Landsat products are of three different categories. They are Tier 1, Tier 2, and real-time data products. So tiers, in other words, are the categories. And in each collection, we have TOA, that is top of atmosphere reflectance. We have surface reflectance, and we have land surface temperature. And similar is the case for Landsat 4, 5, 7, and 8. So the very first data product types are the ROSINs. These are the ROSINs are available in digital numbers, and they represent something called scaled radians. And these digital numbers, or DNs, is converted to the sensor radians from the linear transformation. The coefficients are used, which is already stored in scene metadata. So in Earth Engine, we have ee.algorithms.landsat.calibrated radians, and what it does, it converts digital numbers to the sensor radians. So we have the raw image here, and we have centered at the centered, and the zoom level is 10. We have added it as layer, band 4, band 3, and band 2. This is the raw image, and this has been converted to radians, and then after it can be layered. And raw data can also be converted to top of atmosphere reflectance. That can be done through ee.algorithms.landsat.toa, and that converts the raw data to top of atmosphere reflectance. However, we do not need to be converting this every time, because Earth Engine already contains different data products related to it, and this is just to understand that the algorithms are also present in Earth Engine. So here we have the different products. These are the surface reflectance, and Landsat surface reflectance are generated from different algorithms. Here, Landsat 4, 5, and 7 are generated from LEDPS algorithm, and for Landsat 8, surface reflectance data, YALI-SRC algorithm is used. So these all are provided from USGS level 2, tied to level 2 Landsat data. So this is just the showing of the codes that they are present here. And there is also something called simple cloud score, and this is the cloud scoring algorithms. We generate this from the ee.algorithms.landsat.simple cloud score, and what it does is it is helpful to mask the clouds. And by masking, we're not actually completely removing the clouds, but this algorithm helps us to calculate or generate those cloud score, and these cloud score would not be used in the other other calculations or other procedures. So here we have the e.algorithms.landsat.simple cloud score, and here we create the mask based on that. So masking generally is used when we don't want those pixels to be calculated, or we don't want to use them in our analysis. So we have the cloud score less than 20, and we update the mask by .update mask. And we also have this sensor ID, and when we are mosaicing different Landsat images, sometimes the error is generated, So the sensor ID is particularly used to generate the mosaic, and the sensor ID property is specifically mentioned. And we also have the simple composite. For that, we have the ee.algorithms Landsat Landsat.simple composite. This is the collection. In the collection, we are applying this algorithm, and what it does, it selects a subset of scenes, converts to TOE reflectance, and applies some simple cloud score, and takes the median values of the least cloudy pixels. So here, as the median values are taken, completely free from cloud images are formed. So we also can have some custom values. For example, here we have the percentile and cloud score range values like that. So this was the thing related to the different algorithms related to Landsat. So when you run this, so when you run this here, so the very first image here is the raw image, and then after we have the conversion to the radians by here, and the first we converted it to e.algorithms.landsat.calibrated radians, and it appears to be something very weightish kind of effect we have here. And then we converted it to TOA reflectance. So here we have something a little brighter, little reddish or little brighter than before. And after that we have the TOA. This is a cloudy scene. So here we have lots of clouds, and after calculating the simple cloud score, we have the maxed images here. And by maxed, we are not actually removing all the clouds. It is just to avoid those images in our to avoid those pixels in our analysis. So here we have the TOA mosaic. So I believe it has been copied 2 times. I might have copied that 2 times. No problem here. And after we have the TOA composite that we did from ee.algorithms.landsat.simple composite, and we have some custom TOA composite. So for the case of TOA composite, the clouds are removed because we take the median values of all the least cloudy pixels. So this was for the Landsat 8 or Landsat related data products. We also have the algorithms for Sentinel-1. And for Sentinel-1 algorithms, the thing to understand is we have transmitter receiver polarization. They are of dual polarized or single polarized. They may be VV, VH, VVVH, and HHHV. And the instrument mode can be interferometric wide swath mode, that is IW, extra wide swath, that is EW, stripe map, SM. It depends upon the location, but generally in land, IW mode is common. And we also have orbit properties passes, that is when the satellite is descending or when the satellite is ascending. And we also have different resolution meters, that is from 10 meters to 25 meters to 40 meters. And the resolution available is high or medium. So, and for the Earth engine, the images or the datasets available are already pre-processed from Sentinel toolbox. um, and in those images, the orbit file is applied. There's GRD, border noise removal, thermal noise removal, radiometric calibration, terrain correction. These all things that we do, what we do in Sentinel or Snap Toolbox. This has all been done in the Art Engine. So in the Art Engine, when we first load the Sentinel image collection. It is similar to other processes here. And the main thing we need to understand is we can filter it. We can continuously filter it by, here for example, we're filtering it by transmitter, receiver polarization, selecting VV and selecting VH, and instrument mode to be IW. And those has been selected based on ascending or descending. It is just the filtering of the different metadatas. And then after we can calculate the mean. This is for the visualization. This is for ascending. This is for descending. And then after we have the VB selected here for the combined ascending and descending image collection. And then also we have the combined ascending and descending image collections for VH. And this always has been added as layer. And this is simple because we are just filtering it by the metadata, and we are calculating its mean, and then after we are adding them all as the layers. So if you can see here, we have the VV ascending descending mean, VH ascending descending mean, and ascending mean and descending mean. So these are all just the for the visualization. So usually in Sentinel-1, for Sentinel-1, different users or many expert users use different colors, and based on that, the Sentinel-1 images 2 appears as beautiful as any optical images. So it depends. So regarding the different layers, it depends, and much more understanding might be important. Why certain layers appear very dark, and why certain layers appear very brighter. So it depends because there are different properties here. They are descending, ascending, and things like that. So this was a very little information related to Sentinel-1 algorithms. And finally, we have some algorithms related to resampling and reducing resolution. So for this, Art Engine applies nearest neighbor resampling method by default. And the two methods are resample and reduce resolution. And here in the very first image, we have the Landsat images loaded here over the San Francisco, California, US. And we have this set at the center, and we have the visualization parameters. So we're just adding the very first original image, and we have resampled here from the bicubic in the changing it by the bicubic resampling, and that has been added as the new layer. We also have the Morris EVI image. We select the EVI, and we set the center and it antennas layer. And for this, we also can see the projection of the image by Morris.projection, and we want to print it, and the projection related to Morris is global sinusoidal projection. And here we have the forest cover data at 30-meter resolution that has been selected. The tree cover 1000 band has been selected and has been added as forest cover 30-meter, and that has been reprojected as an aggregation. We have selecting the reducer.mean, and that has been scaled and reprojected to similar to the Morris projection. So here, what we're doing is, in simple terms, we are just converting the resolution, or not actually resolution, but the projection of the forest related image to MODIS related projection. So this is the conversion, and we have added it as layer. And similarly, there is the next forest area has been computed, and it has again been aggregated instead of resampling. And here we are doing the same thing, reprojected based on the MODIS projection. So we run this. So the basic idea is here to convert or reproject the forest bands into, or forest rasters into the what the MODIS projection is. So here we can see the MODIS projection is SR over Z6974. It just means global sinusoidal projection. And here we have the different layers. The first layer is, if we check this one out, here we have the very original image, and if we zoomed it, and the very first original image of Landsat is like this very blurry kind of things, but when we have resampled it, it appears a little smooth than before. You can see that one, a little smoother than before. And we also have MODIS EVI here, so the resolution is not that great. However, when we the forest cover at 30 meter, and here forest cover at MODIS scale, and forested area at MODIS scale. So the 30 meter resolution has been reprojected at the MODIS scale. So that is the only thing that we have done, and this has been done just by the we have first identified the reprojection. What is the projection of here? Projection of MODIS is, and that we have applied to the reproject as MODIS projection. So this is the main thing we need to understand. So that has been done. The 30 meter forest cover has been, reprojected to the MODIS scale. So I believe this is it. So the course, or all these courses are available from the guides available at developers.google.com. And this video in particular was an attempt to summarize, of course, to learn and understand more. Of course, the site contains much more better explanation. But even if you are watching this, I believe this was helpful to you. So for this video, this much. See you next time.